Hello guys, good evening. So what have we done last class? Tell me.
So we did Claisen condensation.
Okay. Achha, aldol and Claisen we have done, no? Claisen, I think we have finished. We were about to start Cannizzaro. Yes?
Yes, sir.
Okay. So write down the heading, Cannizzaro reaction. Okay. Cannizzaro reaction is what? It is actually, it is a reaction of, again, aldehyde or ketone. Write down the first point. It is a reaction of aldehyde or ketone with no alpha hydrogen. Means alpha hydrogen is not required here. Okay. We require concentrated base for this purpose. Concentrated base, and this reaction is, it is disproportionation reaction. Disproportionation. It is a disproportionation reaction. Again, we'll take two molecules over here. One get oxidized and other one get reduced. Okay. So for example, you see, if we have okay, so if you have two molecules of formaldehyde, HC double bond OH, so obviously there is no alpha hydrogen present into this. When this you allow to react with concentrated base, that is OH minus, this converts into HC double bond O, O minus Na plus, and CH3OH. This is the reaction we get here. Okay, like I said, Cannizzaro is a disproportionation reaction. So one molecule get oxidized, other one get reduced. We know aldehyde on oxidation gives acid, on reduction gives alcohol. So one molecule of alcohol, one molecule of salt, because the medium is basic, right? So basic medium, we already know that we won't get acid as the product. Carboxylic acid we won't get, right? H plus and OH minus reacts and it forms a salt, and that is what we get here. Right? So easy one. How do we write down the product first of all? The product is, we have HCHO. So one molecule goes under oxidation, so it forms acid, that is HCOH. Right? This is oxidation. This one goes under reduction and this converts into an alcohol. So CS3OH. Keep that in mind. C double bond O on reduction, it converts into CHOH. So instead of C double bond O, I have written CHOH. 2 hydrogen is already present, so CS3OH. This is how the product will write. Okay. Further, the medium is basic, so we know we won't get acid as the final product. So this goes under acid-base reaction with this concentrated base and converts into CS3COO minus. If NaOH here we have, then Na plus we get here. Okay. So we'll get carboxylate ion plus alcohol in this reaction. Okay, we'll see the mechanism.
Sir, could you go back to the previous slide for 1 second?
Just a second.
Sir, is this the mechanism? Sir, is this part of the mechanism?
No, mechanism we'll discuss. This I have discussed how to write down the product. If you know this disproportionation, so one molecule you write down the oxidized product, another one reduced product, right? Molecule answer is this.
Done, sir.
Done? Okay. Now the mechanism you see, the first step of this reaction is the attack of base OH minus on the carbonyl carbon, that is HC double bond OH. Okay. So this O minus attacks onto this carbon, pi electron moves up and it converts into H CO minus H and OH plus nothing. Okay, we'll get this. Now, next step, what happens? This ion that we get in the first step, it releases hydride ion from this. We have O minus H OH. And another molecule we have formaldehyde at C double bond O H. So in this, what happens? This lone pair comes back. This H minus goes out. And this H minus, which comes out, it attacks onto this carbon of the other molecule. And this pi electrons shift onto this carbon. Okay. So here we get H C double bond O OH plus we get H CO minus H H. Correct. Removal of hydrogen here, it is oxidation. The molecule which is releasing hydrogen, it is oxidation of it. And the one which is accepting H plus, it is reduction, getting reduced. Hence, it is disproportionation reaction. Okay. This step is slow and RDS of the reaction. Okay. After this, it is simple. This O minus protonates from this hydrogen and this converts into HC double bond O minus ion plus It is CH3OH molecule. Done. So suppose we have one molecule like this. Always we take two molecules of this. Remember that. With no alpha hydrogen. For example, we have H C double bond OPH with concentrated base, concentrated OH minus. One molecule will get oxidized, two molecules of this. So we'll get HC double bond O, C double bond O. Oh, sorry, H, we have pH here, no? Because hydrogen will shift onto the other molecule. So we have pH, C double bond O, O minus, plus we'll get pH, one H we already have, C double bond O converts into CHOH. So CH and H, it is CH2OH. Did you get it? Any doubt in this? Done. What is the product we get in this one? This one. The product would be, one would be an ion, carboxylate ion, that is C double bond O, O minus, and other one would be the alcohol, which is this. And instead of C double bond O, what we'll write? We'll write CHOH, correct? And one H we already have, so CH2OH will get here. No doubt in this? Just a second, guys, I'm getting an important call. Yes, done. Now you look at this molecule here, this reaction, and write down the product in this one. Suppose we have hydrogen one side, then C double bond O and D with concentrated base OH minus. Tell me here what we get.
CH3OD and HC double bond.
CH3OD. Which bond is easier to break? Tell me.
1 second, sir. I think it should be
See what happens.
HC4.
Look at the mechanism first of all. What happens if I briefly explain you the mechanism? This OH minus comes over here. This pi electron goes up, and when this comes back, then one of these bond breaks, right? Carbon hydrogen or carbon deuterium. So which bond is easier to break? That depends upon the bond energy of the two bonds. And we know the bond energy of CH bond is lesser than the bond energy of CD bond. That's why CH bond is easier to break. This is the order we have. Bond energy of CT. Bond length is ulta of it. Okay. Bond length is maximum in CH. That's why the bond energy is least. And hence, you see in CH3, it shows more hyperconjugation than CT3 because the bond length is more easier to break the bond, right? So if you compare this carbon hydrogen bond and carbon deuterium bond, CH bond is easier to break, and hence in the oxidized product, we don't have this hydrogen present, because if you look at the mechanism, the last reaction you see, the mechanism, the molecule on which this OH minus attacks, that goes under oxidation. Okay, so this attacks over here, this molecule will get oxidized, right? Pi electron moves up, forms a pi bond again, then one of the bond breaks, carbon hydrogen bond is easier to break, so this deuterium will be there as it is. We have C double bond O, and instead of OH, we have O minus here, right? And the other one would be the reduced product DCH2OH. This is the product we get here. Any doubt in this? No doubt. See this one. HC double bond OH plus see, in this reaction, we have two different molecules, right? So the name of this reaction is cross Cannizzaro. Exactly same thing, like cross Claisen, cross aldol. This one we are taking two different molecules. So it is first of all cross Cannizzaro reaction. Okay. Now in this one thing you have to understand that since we are two different molecules, so if this OH minus attacks on this carbon, it gives you one particular product. If this OH minus attacks on this carbon, it gives the another product, right? So basically the molecule on which OH minus attacks, that goes under oxidation, right? So whether we get oxidized product with respect to this molecule or this molecule, that's the question, right? So which one we should take for oxidized product?
So the first one, formaldehyde.
Formaldehyde. Why?
So the delta plus there is not very stable, and the other one there's resonance. So
Yes, correct, correct. Another thing, you can talk about the positive charge stability of that, right? This delta positive is resonance stabilized. Here we do not have such case, similar cases here. another thing is what, when OH minus attacks onto this carbon, it feels a bit of repulsion because of this bulky group, correct? Relatively we are talking about, but here we do not have any bulkiness, right? Hydrogen small elements. So attack of OH minus on formaldehyde is always easier, right? This attacks onto this carbon, right? It is always easier to attack onto this formaldehyde. That's why one point you must remember here, very important, this one. Okay, generally formaldehyde based question they ask in the exam, that whenever formaldehyde present in Cannizzaro reaction, OH minus always attacks on formaldehyde, because here the hindrance is the least. Okay, it always attacks onto this formaldehyde, and hence formaldehyde always goes under oxidation. So we'll get here oxidized product with respect to formaldehyde, and whatever other molecules we have, that gives you the reduced product. Here we have CH2OH. Any doubt in this? Write down this note here. When formaldehyde present, as one of the aldehyde, when formaldehyde is present as one of the aldehyde, then OH minus, or the base, then OH minus attacks on formaldehyde and gives oxidized product. In all this, you see there we do not have any alpha hydrogen, right? So formaldehyde goes under oxidation, plus this is the product we get. Okay.
So 1 second, can you just go back?
Your duty is over. School exams.
Yes, sir.
Thank you, sir.
Okay. Yeah. Now you see the next one is, it is intramolecular Cannizzaro. Intramolecular Cannizzaro reaction. Okay, so in this one, we do not take two molecules because it is intramolecular. So two carbonyl group present in the same molecule. For example, this one. Concentrated base. Okay, so two molecules, we have two part we have. So one part will go under oxidation, for example, this minus, and other part will go under reduction, so CH2OH. This is the product in this reaction. Okay, if you want to see the mechanism here, OH minus attacks, suppose, on this carbon, because both are symmetrical carbon we have. It attacks on this carbon, pi electron shift, and then it converts into HC, O minus OH, C double bond O, H. Exactly same mechanism here we have. Now, when this lone pair forms pi, H minus comes out, and this H minus attacks on this carbon in the same molecule, and this pi electron shift onto this oxygen. So it converts into C double bond O, OH, then C double bond O, H, and H, not single bond O. Here we have O minus and H. And then this O minus protonates from this OH, converts into C double bond O, O minus, COH, H2. This is the product we get. So within the molecule it happens, similar kind of mechanism, and the product is this. Okay, so it is symmetrical. Wherever this OH minus attacks, you'll get this molecule only. Okay, copy this down. I'll give you some more examples here. No, other living group, then it won't be an aldehyde or ketone model. That will be probably anhydride, ester, or acyl halide. But this reaction is given by aldehyde and ketone only. So we cannot consider that. Varun. Okay, so all these are named reactions. You should know with what compound or molecules gives this kind of reaction. Like aldol and Cannizzaro is given by aldehyde or ketone. Claisen is given by esters. Okay, so this you have to memorize. Now you see this example here. We have intramolecular, so H, C double bond O, then C double bond O, pH. Tell me the product into this one, concentrated base. And one more, the last one, H, C double bond O, C double bond O, D, and the same reagent. Okay, so where this OH minus attacks in the first one? In the first one, OH minus attacks on the carbon atom from which H minus goes out, this carbon, right? And this H minus comes onto this carbon atom. So here the product would be, I'll write down it directly, will have C double bond O, O minus. Wherever OH minus attack, that will go under oxidation. So this attacks onto this carbon, means this part goes under oxidation, so CO, O minus. The other part goes under reduction, so it is CH, OH, pH. This is the compound. Yeah. Yeah, that is right. Correct. Okay. Similarly, here what happens? The OH minus, it attacks on the carbon atom, which has the weaker bond, right? That is again this one, because CH bond is easier to break. So this attacks onto this. So this part goes under oxidation. So it is C double bond O, O minus, and this part goes under reduction. So CH, D, and H. This is the product we get. Right, so just in cross, just you need to identify first that where OH minus should attack. It will attack on the carbon atom, which is less sterically hindered, right? And that carbon goes under oxidation. That is. Okay, so this is it for Cannizzaro reaction. Now the next one, write down the next reaction we have. That is haloform reaction. See, haloform reactions are those reactions in which the products are, one of the product is haloform. Okay, so the product forms in this reaction. Product forms in this reaction is CHX3. For example, we can get CHCl3. We can get CHBr3, bromoform. We can get CHI3, that is iodoform. If these product forms which means the reaction is haloform reaction, right? This is chloroform. This is bromoform. The color of CHI3 is yellow. CHCl3 is colorless liquid. CHBr3 is pale yellow. This one is colorless liquid. Not important the color here. Just I have given you. Write down, this reaction is given by the molecule which has methyl keto group. Methyl keto group means we have C double bond O ketone, and one side we have methyl present. If this group is present, then the molecule gives positive haloform test or iodoform test or haloform reaction. Okay, it's not like only ketone gives this kind of reaction. There are other molecules also. We'll see those molecules. Okay, what are molecules can give this kind of reaction? Because this question also they ask in the exam, that which molecules gives haloform reaction or gives iodoform test. Okay, so what are those molecules? We'll see that later. First of all, we'll try to understand the reaction here. Correct. So for example, you see, if the reaction is RC double bond O, CH3, and this is allowed to react with I2 in presence of NaOH base. Okay, I2 with NaOH in presence of base. This is haloform reaction. The reagent is halogen in presence of a base. The reaction of halogen also possible in presence of an acid, but that reaction is not haloform, that's a different reaction, but that is also important. We'll see what product we get when the medium is acidic. Here we see what product we get when the medium is basic. Okay, I2 with NaOH. So the product we get here is RC double bond O, O minus Na plus CHI3. This is how iodoform forms in this reaction, and we say the molecule gives positive iodoform test. Okay, copy this down. I'll just write down the mechanism in the next page. Done. Okay. Now, let's discuss the mechanism of this reaction. We have RC double bond OCH3 and NaOH is the base, OH minus. This OH minus takes this H plus, the alpha hydrogen here, and it converts into RC double bond OCH2 negative charge, right? Plus we get H2O. So this is acid-base reaction. Okay. Now in the second step, what happens? This conjugate base RC double bond O CH2 negative. This reacts with iodine I2 molecule. It basically attacks onto this iodine and I minus goes out from this, converts into RC double bond O CH2I plus I minus. Okay. Second step, which is also similar to the first step. RC double bond O, we have CH2I plus OH minus. It converts into RC double bond O CHI2 negative charge plus we get here H2O. Okay, Oh, what did I write? Not I2 we won't get here, CHI. I2 we get in the next step, okay? So in the next step, what happens? This is the base. So RC double bond O, CH negative I2, and this reacts with iodine. Again, it takes this iodine, I minus goes out, it converts into RC double bond O, CH I2 plus will get I minus here. Same thing happens in third step. RC double bond O, CHI2 with OH minus converts into RCI2 just a second. C double bond O, CI2 negative and H2O. All these steps are same. And in the next step, again one iodine attached to the negative charged carbon, CI2 negative charged carbon plus I2 converts into RC double bond O, CI3 plus I minus. So these are the first steps actually. In the first step, this happens. Copy this down first. Done? Okay, now one question that they asked, the reaction is not complete yet. Okay, we'll discuss one question that they asked from this. This is the first step is this, where we get CI3. And in the first step, we have 3 sub-steps, right? 1, 2, and 3. So the first step that you have here, suppose the rate of this reaction is R1, this is R2, this is R3 here. So what is the order of this R1, R2, and R3? Rate of these steps, which one is maximum, which one is minimum?
So is the third one the most fastest?
Okay, and why is that so?
So that conjugate part will be stable. The conjugate is because of minus I effect.
You can say that. Yes, you can say that. Other thing is what? Because of iodine present here, the hydrogen becomes more acidic. Yes or no? Minus I effect of iodine. And it is easier to remove this H plus for this basis, right? So that's why this can extract this H plus easily and the reaction goes with a faster rate, correct? In each step you see, here we do not have any minus I effect. Here we have 1 minus I, here we have 2 minus I. So if you compare the rate of this reaction 1, 2, and 3, the first one has the least rate, R3 is maximum, then we have R2, and then we have R1 because of the minus I effect of iodine. So point I'm trying to make that in each step, the rate of the reaction is increasing. Here we have some rate, then it increases, and then again it increases, right? That's why the reaction, if it starts from this, it goes till here, till this point, okay? Fine, that's the one thing. Obviously, we must have enough of I2 present here. 3 equivalent we required, enough of I2 is present, then the reaction goes till here. If only one equivalent is there, then the reaction stops over here because for the further steps, for the next step, I2 is not present. So we have this here. Now, this is the first step of the reaction. Rate of the reaction we have already discussed. In the last step, what happens? We get here RC double bond O and CI3. And we have base OH minus. Now, this base OH minus has taken all the acidic hydrogen. We do not have any acidic hydrogen present here. So this OH minus attacks onto this carbon, the carbonyl carbon. Correct? And when it attacks onto the carbonyl carbon, this pi electron shift here, and this OH will get attached to this. So RC double bond, single bond O minus, right? CI3 and OH. Next step, could you tell me what happens in next step?
So the hydrogen from oxygen will go and, CI3 leaves.
Yes, when it comes back, this CI3 leaves because CI3 minus is a good leaving group because of 3 minus I effect, iodine here. Sorry. Right, we have 3 minus I effect. So CI3 minus leaves from this and it converts into RC double bond O OH. Again, it's a simple step. We have proton exchange because the basic medium we have acid won't form. This H plus comes over here and it converts into CHI3 ido form plus we get RC double bond O minus. Clear? So all those molecules which forms CHI3, we say it gives positive iodoform test. Done. See, since CI3 is forming here, that's why 3 hydrogen is required. Then only one by one, the hydrogen goes out and it forms CI3 here. If 3 hydrogen is not present, this won't form. That's why the condition is methyl keto group. Okay, that's the one part. Okay, now write down iodoform test is given by iodoform test is given by Iodoform, okay, iodoform test is given by, like I said, we need methyl keto group for this. So CS3 C double bond OH, the simplest one, gives positive iodoform test. If you have CS3 C double bond O CS3, this also gives positive iodoform test. If you have benzene ring with C double bond O CS3, gives positive iodoform test. We just need this group, COCS3 group, right? Positive iodoform test. It's not like only aldehyde or ketone gives this reaction. Okay, I've given you some example of aldehyde or ketone, but it is not like only aldehyde and ketone. Write down, apart from this, all alcohol, apart from this, all alcohol which on oxidation apart from this, all alcohol which on oxidation gives methyl keto group shows this test. Okay, for example, we know 2-degree alcohol on oxidation gives ketone. So if you take this one, 2-degree alcohol, and one side we have methyl. So obviously if it goes under oxidation, it converts into RC double bond OCS3, and hence this gives positive iodoform test, this one. So this also gives positive iodoform test. It's like the tolerance reagent test. Fructose has this thing, keto group, but since it converts into one part of it converts into aldehyde, right? Hence fructose also gives tolerance reagent test. Similar thing we have here. 2-degree alcohol, one side we have methyl. If on oxidation it gives methyl keto, right? Then it gives positive iodoform test, correct? 1-degree alcohol if you have, this is for 2-degree alcohol. Now suppose we have 1-degree alcohol, for example, CH3, CH2, OH, 1-degree alcohol. If you oxidize this, what we get here, could you tell me? If we oxidize this?
So it depends
Okay,
if it's
you'll
strong
get-
or mild.
The mild oxidation will get aldehyde.
No, I am considering only till aldehyde, not complete oxidation. Right, so it converts into what?
Phenol.
CH3CHO. Right, you see here again, methyl and CO group present. This gives iodoform test. This also gives iodoform test. Condition is we must have this CH3 present. If you have C2H5 here, this won't show. Right, that is the condition. Similarly, you see pH, CH3. This side we have CH3, OH with this. So pH, C double bond O, CH3 it forms. This gives, and hence this also gives. So this kind of questions, alcohol related questions, important. Okay, sometimes they give you 8 to 10 structures. They'll ask you how many structures gives positive iodoform test. These things you keep in mind. Apart from this, some alkyl halide also shows this test. So write down alkyl halide. Alkyl halide which forms alcohol which on oxidation gives methyl keto, also shows this test. For example, CH3 is mandatory one side, CH, PH, Cl you have here, this with I2NaOH, it converts into CH3, CH, PH, OH. So this gives This also gives. Okay, all these reactions are very, very important. I'll give you some more example here in iodoform test, right? Some different examples which shows iodoform test here. Like you see this one. CH3, C double bond O, CH2, C double bond O, CH3. Does this show iodoform test? I2 with NaOH. Could you tell me the product in this reaction? No, it's not. See, aldol is, you cannot consider origin here because for aldol we don't need I2 there. Okay, so aldol is not possible.
So, but can't we say like NaOH is there? So it'll do self aldol and then that can go.
No, no, no. Self aldol or aldol you consider when you have only base, that to dilute.
So here NaOH is like not dilute.
No, here we don't doubt. See, usually very dilute base we don't take here. We cannot say very concentrated, but you can say somewhere around, moderate to concentration base. In that range we take, not dilute. Basically, we don't talk about here whether we are taking dilute base or concentrated base. I2 in presence of a base. But yes, if you have to choose the one, we'll go for, concentrated base or more than, moderate, like that, in that range, moderate and concentrated base, in that range we'll take here.
Okay, sir.
Close to the concentrated base we have here. Even if you take dilute also, Ruchir, then since I2 is there, so I2 is not the reagent of aldol. So you cannot consider aldol here.
Okay.
Okay, you see what happens here. First of all, you tell me, first reaction is what? The attack of OH minus takes this acidic hydrogen. So which hydrogen it will take? OH minus? So from where this OH minus takes H plus, because we have three different positions.
So it'll take it from the middle CH2.
Why middle CH2? That's right, but why middle CH2?
Both of the COOs on both of the sides, like that C is delta plus, so it has a minus I effect.
Correct. So this one is, if you remember, we have discussed this in tautomerism, that this is active methylene group. Both sides we have electron withdrawing group present, and hence the two hydrogen becomes highly acidic, more acidic than these hydrogens, right? So obviously this base will take this H in the first step, and it converts into what? It converts into CH3, C double bond O, CH negative, C double bond O, CH3, which then reacts with I2 and it converts into CH3, C double bond O, CHI, C double bond O, CH3. Correct? Same thing happens again. I'll write down in one step here. First step with base, second step with I2 converts into CH3CO whole twice CI2. Is it correct? Yes. Okay. Now you see in the next step what happens. We have this molecule CH3 C double bond O.
Wait, sir, could you move back to the previous slide?
Yeah, just a second. C double bond O, CH3. And again we have base OH minus.
Done, sir.
Done? Okay.
Yes, sir.
So next step you see, this is the reaction. Now this OH minus, the base, this will attack on any one of the carbonyl carbon depending upon the hindrance. Here we have similar thing. So anywhere it attacks, gives you the same product. This pi shift on to the oxygen and the product here is CH3, C double bond O, CI2, CO minus, CH3, and here we have OH. In the next step, when this pi electron lone pair converts into pi here, then this goes out as a leaving group. Ci2 minus is quite stable, minus I of iodine and resonance with C double bond O. So it can easily go out as a leaving group. So C double bond O, Ci2 negative, plus we get here CH3, C double bond O, OH. Right, then what happens? Could you tell me after this? After this? Then this H protonates this carbon, intramolecular. Sorry, this H and this proton exchange, not intramolecular. So what it gives? CH3, C double bond O, CHI2 plus CH3, C double bond O, O minus. Acid won't form in basic medium, we'll get this. Now this one we have already done. It again reacts with OH minus and then I2. So it converts into what? Final reaction, I'm writing it down. It is CHI3 plus CH3, C double bond O, O minus. Tell me, is it correct?
So why did OH minus attack on the carbonyl carbon? There's an alpha hydrogen, right? To the right of the carbon.
Yes. But you're talking about this one, no? This one you're talking about, right?
Yes, sir.
See, we have two minus I group iodine, right? It's very competitive here, right? 2 minus I group is attached. then the positive charge density on this carbon and this carbon increases a bit, right? And that facilitate the attack of OH minus on this carbon atom because of 2 minus I effect attached onto this carbon.
Okay, sir.
Theoretically, if you see, you can think of this OH minus will take this hydrogen here. But what is happening practically, that you have to consider. Practically what happens, this attacks onto this. And how do we explain this? Because of the 2 minus I group that is present here. It increases the positive charge density on these two carbon atoms. Hence, base can easily attack onto this carbon atom.
Okay, sir.
You understood this? Right. So how many equivalent of I2 we are using for this reaction from beginning to end? How many we are using? 3?
Yes, sir.
3 we are using, okay? So we are using 3 equivalents of iodine for this, okay? Reaction is, if you look at this reaction, obviously you will see CS3CO is present, so it will show iodoform test. But always remember, it is not showing iodoform. The reaction is not taking here at the terminal carbon. It is taking place at the what we say, the middle carbon here, right? Which is the active methylene group, correct? And after this, it converts into CS3COCHI2. Further, the reaction takes place to convert this. So final product will be 2 molecules of acetate ion and iodoform. Since iodoform forms in this reaction, the molecule gives positive iodoform test. Okay. One note you write down, esters and carboxylic acid does not give this test. Esters and carboxylic acid does not give this test. Done? Okay. These examples you see, does this show iodoform test? Yes, tell me. The first two. Does this show iodoform test?
So yes, sir.
Right? The first one is alcohol, 2-degree alcohol, it converts into ketone. The first one shows, second one also shows, right? So basically, you just keep this in mind that whenever you have active methylene group present like this, and two side we have keto group, this shows and this also shows. Same thing we have here, right? In this, what happens if the reaction takes place? This goes under a nucleophilic addition reaction, right? It attacks onto this CH2, it converts O minus OH and OCH3. And then what happens? This comes back, this goes out as a leaving group. It converts into CH3, C double bond O, OH. And then H plus comes out, gives you carboxylate ion, right? So reaction, this is not giving iodoform. The reaction is not taking place here at this carbon atom because of the leaving group present, okay? Hence this ester does not show iodoform test. Same thing happens with this. It gives acid-base reaction with acid. Acid-base reaction. OH minus takes this H plus, converts into CH3, C double bond O, O minus, plus H2. Right, so acid and ester does not give iodoform test. You must remember this. Okay. Now you see this one.
So what's the final product for the second question?
Second question, just a second, I'll go back. C double bond O CS3 and this with I2 NaOH. This is iodoform reaction. And we are heating this also. This is different. We are heating it. Okay, we'll do this. Just let me go back. Which one, Param? This one?
Yes, sir.
Okay. Could you write down the product, the final product in this reaction? See, I'll give you an idea. We have this.
Like open the chain and then one carbon becomes iodoform and then get two carboxylic acids on the sides.
You'll get this.
Yes, sir.
Correct?
Yeah.
And then OH minus comes here. This goes up. So it converts into this one. O minus OH. And here we have 2I2 double bond O, correct? Now when it comes back, so this goes out, leaving group. So we'll have here this carbon, and here we have 2 iodine. Okay. Is it right? 1, 2, 3, 4. One more carbon atom we'll have here. Just a second. I'll just correct it. So here we have like this, okay? And here we have double bond O. Double bond O, OH. Then what happens is H comes over here. Okay, we get here H, and then again, this is taken up by OH minus, we'll get CI3 here finally. C. So I'll get CI3, double bond O. Here we have double bond O, O minus. Is it right now? Till here it's fine?
Yes, sir.
Then what happens? The base OH minus is it attacks onto this carbon. This comes over here. And when this forms a pi bond, this goes out as a leaving group, correct? So this converts into 1, 2, 3, 4, right? Double bond O and OH here. This we have double bond O, O minus, plus we get here C I3, which takes hydrogen from this and converts into dicarboxylate ion plus CHI3. Is it clear?
Yes, sir.
Okay. So this is the product we get into this one if you do this reaction. Try this one and tell me the product here. Cyclohexanone and carbon dioxide. Okay. That's okay. Let's see this. So obviously we have COCS3 here. So this group shows iodoform test, and you can consider this as R group, right? COCS3. So it converts into R as it is, C double bond O, and CS3 will get here O minus Na plus, and CS3 will get CHI3, iodoform. So first of all, it shows iodoform test. Now, if you look at this reaction, this molecule is alpha and beta. It is beta keto carboxylate ion, or beta keto acid we do not have. But whenever we have beta keto carboxylate ion or beta keto acid and you are heating it. So whenever you heat these kind of compounds where at beta position we have keto group present, then CO2 eliminates from this. CO2 eliminates and rest molecule will be as it is. This would be as it is and CO2 eliminates here. Right. So this we call it as alpha beta, right? Beta keto carboxylate ion. This one is, but this is true for beta keto carboxylic acid. Remember always, when at beta position keto group is present and you are heating it, then the molecule eliminates CO2 and converts into a ketone. Like this. It's very important. One note you write down: beta keto compounds on heating eliminates carbon dioxide. Okay. Correct. Now, the next reaction is, this is iodoform reaction we have done. So must remember all what kind of compounds gives iodoform test and these products that we get here. Next one, write down alpha halogenation reaction. Means halogenation at alpha position. Alpha halogenation. Alpha halogenation is possible in both acidic as well as basic medium. Possible in acidic and basic medium. Okay, both important here. So basic medium reaction we have already seen, that is I2 with NaOH. Okay, same mechanism we have here. So we are going to discuss here the acidic medium, mechanism of acidic medium. In acidic medium, what we do whenever you have an aldehyde or ketone, halogenation, suppose I2 in presence of acid H+. So what we do, we always consider the enol form of this molecule. Like this is a molecule given. So we'll write down the enol form of it. CS3 C double bond O H, and the enol form of this is CH2 double bond C OH. Okay. Now this behaves as a nucleophile and attacks onto this iodine. So in the next step, what happens, you see, we have CH2 double bond C OHH plus I2. This pi electron comes over here, it takes this iodine and I minus go out from this. Product is CH2I COH H positive charge, and we get I minus from this. Now, if you look at this carbocation, this can form easily because this carbocation is resonance stabilized. Yes or no?
Yes, sir.
Resonance stabilized. Oxygen has lone pair on it, so resonance stabilized. Correct? So finally from this, H plus comes out and it converts into CH2I C double bond O H. So we started with this CH3COH and ends up with this. If you compare this, it is the alpha halogenated product. Yes or no? Did you get it? At alpha position, iodine get attached. So that is the alpha halogenation. Yes. But you can think of Further, the reaction of acid with this, suppose we have this molecule that we get in the first step, ICH2, C double bond OH. We can further consider the tautomer of it. This comes over here, this comes over here, it takes this hydrogen and it converts into CH double bond COH and H. Clear? Yeah, Roger, just a second. Let me just do this. Okay. So you can ask me, sir, why not this? We have two hydrogen here. This further write down this, tautomer of it. And then this again reacts with the iodine, like this one, you see. CH double bond COH H and plus another iodine molecule. Same mechanism, you see. This comes over here. This attacks onto this iodine goes out, and finally we get ICH, ICOH, positive charge and H, and then it converts into CH2, C double bond OH and H plus. This is what we get. But the problem in this particular step is what? That the carbocation that we get here, this carbocation is highly unstable carbocation. Highly unstable. However, we have resonance possible here. But since we have two iodine group attached, so this destabilizes the carbocation. And the rate of this reaction is extremely slow. Hence, we do not consider this reaction. If this is not possible, this is also not possible. So we can consider here that this reaction effectively takes place till this point, which is the alpha halogenation reaction. Copy this. Done? Richard?
Yes, sir.
Okay. This one also you write down, this step also, all of you. Let me know once you're done. Okay. One note here you write down. this carbocation write down. The carbocation forms in this step. The carbocation forms here is highly unstable. Is highly unstable because of the minus I effect of iodine. Hence, the reaction becomes extremely slow. And we do not consider this reaction. Okay, okay. Okay, now you see this two comparison here. Now we are doing this acidic medium reaction, correct? So what we do in acidic medium reaction, we write down the enol form of it. So CH3, C double bond OH we have. So for acidic medium reaction, we'll write down the enol form, means we are writing it down, we are writing down the alkene here, like this. So we always try to write most stable alkene. Most stable possible alkene when the medium is acidic. And then we consider the reaction here. Always keep that in mind. More stable alkene we'll write down here. But if the medium is basic, OH minus, then what we do, this OH minus take this H plus, we'll write down CH2 negative, C double bond OH, and then on this, the reaction of iodine takes place. It converts into CH2I and CHO. Yes or no? Right. So what is important, that if the medium is basic, then we'll write down the stable carbon ion, negative charge. Okay. Basic medium, we need stable carbon ion. With this, we'll write down the product. Acidic medium, we need stable alkene for the formation of product. Okay. Remember, the reaction of iodoform is two more steps you have to consider here. You'll get CHI3 and other things, correct? But we are not talking about here iodoform reaction. This reaction is the halogenation of this in basic medium. Just will stop till here. Only one equivalent of I2 we are using, right? If you use 3 equivalent of iodine here in basic medium, it gives iodoform reaction. But that is not the case because we are using only one equivalent of iodine in order to get alpha halogenated product. Understood this?
Yes, sir.
Okay. Understood this? Based on this two information, that basic medium, we need stable carbon ion, acidic medium, we need stable alkene. Based on these two information, we'll write down the product in any reaction. Now you look at some examples on this. Okay. Write down the product here. Molecule is given is this. This is I2 with NaOH basic medium and one equivalent we are considering. This is I2 with H plus one equivalent. Write down the product in the two reactions. So are you done with this? See, this is the basic medium. So what we need to write? We need to write down the stable carbon ion. Two possible carbon ion you can think of here. One is this, double bond O will be as it is. One is this, and the other one is the other alpha carbon, which is this. Now, which one is more stable? Obviously, the second one is more stable. This one is less stable. So this won't form, and we'll write down the product according to this. So base forms here, and then this takes iodine from I2, and it converts into a double bond O on the top would be as it is. This methyl and this iodine will be here. Any doubt in this? No. Now, when the medium is acidic here, then we can draw the tautomer of this molecule. So two possible tautomer we have. One is this OH and methyl group here. Another possible tautomer is this side we have double bond OH and methyl group here. Now, which alkene is more stable? First one or the second one?
First one.
First one is more stable, more substituted alkene, right? This alkene is more stable, this won't form, and we'll write down the product according to this. So how do we write down the product? I2 It reacts with I2. You see here. Yeah, you need to be a bit careful here. I2 is here. This pi electron comes over here. This takes this iodine. I minus goes out. Okay. This shifts here. Why? Because this positive charge is more stable, right? This positive charge is resonance stabilized here, and that only eliminates H plus from this. Correct. So this comes over here. We'll get a positive charge here. So here we have OH. I'm sorry. We have OH positive, one methyl, one iodine, and then finally what happens? H plus comes out, double bond O will get on the top, and the molecule is this. Any doubt in this too? Okay, so this is the two things you have to keep in mind. Basic medium, more stable anion. Acidic medium, more stable alkene. You have to draw, right? And it is not always true that whatever product you get in basic medium, right, that would be the minor product in acidic medium. Like minor product we can think of when this iodine attached this side, right? So this is the major, and this major in acidic it becomes minor, right? This is the major in acidic, it becomes minor in basic medium, correct? But this thing is not always true. It's not always true that the major product in acidic medium, sorry, basic medium becomes minor in acidic or vice versa. Okay, it is not always true. It completely depends upon the structure of the molecule given. For example, I'll show you one more example here. With this, you'll understand this particular thing I'm talking about. Suppose you have a molecule, which is this double bond O, and we have NO2 here. Now this reacts with OH minus I2, and I'm considering one equivalent, okay, for both the reaction. Here we have I2, H plus, one equivalent. Write down the product in this two. Okay. Okay, so the product in this two you'll get, you see the carbon ion here is more stable, right? Because of minus M effect of NO2. So I'm writing down the intermediate as well here. NO2, basic medium is there. So negative charge, this one is more stable, this will form. And hence the iodine attach at this carbon. Double bond O and O2 and iodine will get attached over here. Okay. Acidic medium, so we have to write down the more stable alkene. So that would be double bond O. OH will have there. So we have OH, double bond NO2. This is the more stable alkene. And then with the same mechanism, iodine will get attached at the same carbon where NO2 is present, which is this and double bond. Right. So you see in both mechanism, we are getting the same molecule as the product, right? So you cannot generalize this, that basic medium, the major product becomes minor in acidic or vice versa. Okay. It completely depends upon that what is the structure given in the molecule. Okay. Is it clear?
So in this we're just comparing the alpha hydrogen, right, sir, for the tautomer, the enol form?
Yes, yes. Tautomer will write down like this, you see. Either you can shift this hydrogen here or this hydrogen here, alpha hydrogen, correct? So if you shift this hydrogen here, we'll get a double bond here, which is less substituted. This bond comes over here. This pi bond comes over here. This H plus will get attached to this oxygen, we'll get this.
Yes, sir.
Yeah. Okay. Right. So these two, information you must take care of. Alpha halogenation. Alpha halogenation in basic medium is same mechanism as we have in chloroform reaction, haloform reaction. But the only difference is for haloform, we'll take 3 moles. For halogenation, we'll take only 1 mole, right? Okay. Next reaction, the name reaction we are going to do is Perkin reaction. Perkin, Perkin reaction. Perkin reaction, again, it is a reaction of benzaldehyde. Okay. So benzaldehyde reacts with an anhydride in this reaction. Right? It's the name reaction. So these things are fixed. Reaction of benzaldehyde plus anhydride. Anhydride, we can take anything. Like for example, I'm taking this one, CH3, C double bond O, OC double bond O, CH3. This converts into CH3. Oh, sorry. See, one thing here is what in Perkin reaction, what is the leaving group here? What is the leaving group? Leaving group is OCOCH3. This is the leaving group. Right. So like Claisen condensation, this leaving group we consider as a base here. Right. So OCOCH3 is the leaving group here. So the base would be for this reaction is CH3, C double bond O, ONA or O minus Na plus. Right. In the second step, we have acidic hydrolysis and then we are heating it. This is the reagent we have. So Perkin reaction, first step is the base we'll take, and the base depends upon the leaving group we have in the molecule. And in the second step, we have acidic hydrolysis and we are heating it. Right. The product we get here is cinnamic acid, that is pH, CH double bond CH, COOH. Okay, how this reaction proceeds, you look at the mechanism. The first step, we have the base CH3, C double bond O, O minus. Okay, this base reacts with the anhydride, which has hydrogen CH2 C double bond O, O C double bond O, CH3. Okay, so this base takes this hydrogen, converts into CH3 COOH, CH3 COOH, and forms a nucleophile, which is CH2 negative, C double bond O, O C double bond O, CH3. This nucleophile attacks on the benzaldehyde in the next step. So PH C double bond OH, CH2 C double bond O, O C double bond O, CH3. This attacks on this carbon, pi electron goes up, okay, and it converts into PHC O minus H, CH2 C double bond O, O C double bond O, CH3. Is it clear? Yes, Ruchir, go ahead.
So isn't that attack like very tough because the delta positive, we can say it's in resonance.
See, but we do not have any other possibility, no? What is the other possible reaction we have? You can see, depending upon the availability of the charge on the carbon there, you can talk about the rate of the reaction. That you can talk about the rate of the reaction here and in Claisen condensation, which one has a more rate of reaction, that we can talk about. But we do not have any other possibilities. We have to write down the product here into this. We can say the rate is low, right? But the product may form like this.
Okay, sir.
Okay, so this is what the product we get. It is exactly similar to the aldol reaction also, you see. In aldol reaction, what happens after this step, you see, if you remember, the H2O that you get in the first step, right? The H2O that you get in the first step, that protonates the O minus, if you remember, yes or no? That we get beta hydroxyaldehyde or ketone. Remember that? How do you get hydroxy OH at the beta position? The O minus over there gets protonated by the water molecule which forms in the first step. Yes, guys? Remember that? Okay, but here we do not have water, but here we have acid, this one. So this O minus here gets protonated by acid in the next step. This H comes over here, we'll get OH here. And then you are heating it, then we have H plus H2O, reaction takes place here, and then we are heating it, you'll get cinnamic acid. So I'll write down this step in the next slide. First of all, you copy this down. Done? Okay. So the next step, protonation takes place. and it converts into pH, CHOH on the top. We have CH2, C double bond O, OC double bond O, CH3. This again reacts with H plus H2O. This H plus H2O reacts at this position, HOH, right? We can write down the product like this. Simply, you can say first this H plus protonates this oxygen, then the bond breaks. One side will get OH and this side will get acetic acid. So the product here is PH, CHOH, CHH, C double bond OOH plus CH3COH. Okay, and then we are heating it. So it is beta hydroxy we have. So this H2O goes out. So it converts into pH, CH double bond CH, C double bond OOH. This is cinnamic acid.
So what's the name?
CINN AMIC, cinnamic acid. All these mechanisms are very similar. Okay, only the molecule, the reactant and reagents are different. Okay, but when you compare these reactions, aldol, Claisen, you'll be easily memorize all these reactions. Done. Now, write down the product in this reaction. Just one question for practice. We have benzaldehyde, pH C double bond OH, plus the anhydride is CH3CH2, C double bond O, C double bond O, CH2, CH3. Tell me the reagent we should use here. What is the reagent here we should use?
CH3, CH2,
CH3, CH2, C double bond O, O minus, Na plus. And in the next step, it is fixed. We have what? H plus H2O and heating. Tell me the product in this reaction. You can easily compare this with the previous molecule, the anhydride that we are using, and you can easily write down the product. Done? Okay, so here you see the
Yes.
product is pH CH double bond CH3 then what we have CH3 then COOH. This is the product we get. You can write this with the comparison when benzaldehyde is treated with CH3COOCOCH3. So what happens, one of the hydrogen is replaced by CH3 here. So this hydrogen I have also replaced by CH3, which we had in the previous example. Yes, Richard, that's correct. That's what we did. So I would suggest what? I would suggest that one example, the first example that we have done, that you must remember. Okay, keep that in mind. Right. And based on that only, you can write down all the product, because I would, definitely I would, suggest to all of you this, that when you are going to write down the mechanism of all these reactions in the test, you will get confused. It takes time also. You don't have that space so that you can draw the mechanism of all this. So always you try to identify the reaction first, and one, example you just keep this one, benzaldehyde plus CH3COO, COCH3. For that, the product we get is cinnamic acid, PHCH double bond CH3. Keep that in mind. Compare the other reactions with that and write down the product simply. Okay, that is the best way. Okay, so this is Perkin reaction. The another reaction is the next one. Write down. Knovenagal reaction. Knovenagal reaction, will start this after the break. Okay, just name you write down. We'll start this after the break. Okay, we'll resume the session at 6:35. Okay, take a break now. Hello. Yes. So the next reaction we have to start is Knovenagal reaction. Okay. 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 Fine. Knovenagal reaction. Correct. So this is the reaction of, write down. It is a reaction of aldehyde with active methylene group. Okay. Reaction of aldehyde with active methylene group. Okay, active methylene group. Now you see, you have an aldehyde RCHO, and active methylene group, we know we have CH2 is the active methylene group when both side electron withdrawing group is attached. Then it is the active methylene group, right? Z is any electron withdrawing group, correct? First step, this reaction is allowed to take place in a weak base, right? And then we have hydrolysis in presence of acid, H plus H2, right? The product we get here is this R group, you see, this R group. We have this R with CH, double bond CH, COOH. This is the product we get. Okay. In all these reactions, again, I'm telling you, you won't be able to write the mechanism in the exam. It's not like you do not know, hence I'm saying. It's very difficult to write down the mechanism, okay? So always keep this in mind, that how do we get the product, okay? Mechanism we'll discuss, which gives you a better idea of how to write down the product into this. So we have a weak base and acidic hydrolysis. Weak base we take here. Weak base can be pyridine or pipyridine. Pyridine or pipyridine. Pipyridine is this. There's no double bond into this. It is pipyridine. Pyridine, we all know the structure. Okay, benzene with an N present in the ring. Okay, instead of one carbon. So these are the weak base we use for this. Then H plus H2O, acidic hydrolysis. What is Z here? Like I said, it is any electron withdrawing group. Electron withdrawing group. Electron withdrawing group. For example, we can have C double bond O OR. We can have CN, all EWG you can consider. CN, we can have aldehyde, we can have ketone, NO2, all these examples, minus M group. Okay. Copy this down. These two things you must remember. Electron withdrawing group, active methylene group plus aldehyde, the reaction is. How the reaction proceeds, you see, the mechanism here and the product that we get. Can I go to the next slide?
Yes, sir.
Okay. Suppose we have RCHO and this reacts with CH2, and here we have C double bond O OR, C double bond O OR, active methylene group is this electron withdrawing group attached over here. So this, in the first step, we are taking pipyridine. So pipyridine takes this acidic hydrogen, okay, and this converts into what? Again, we have same things, very similar reaction. You will be, you can get it easily. So if this reacts with this pipyridine, so we'll get the conjugate base of this acid, right? So we get here H, C, lone pair negative, CO, OR whole twice, and we get this pipyridine, the conjugate acid of it, H positive charge. Now this base attacks as a nucleophile on aldehyde like this. Now this one is very similar to Perkin. Okay. So what happens? RCO minus H, and here we have CH, C double bond OOR, C double bond OOR. Okay, and then in the next step, H plus H2O. This O minus get protonates with this H plus, and this OR with water, HOH. If I write down like this, HOH, this bond breaks, this bond breaks. So it converts into RCHOH, CH, and both sides we have COOH here like this. So it converts into what? COH, COH, okay, plus 2 molecules of alcohol, ROH we get here. Okay, now we are heating it. So when you heat this, CO2 molecules comes out from this. Okay, and it converts into RCH, OH, CH2, COOH plus CO2. This is again the heating effects. Okay, I'll tell you I'll send you the video for this. Okay, heating effects video. It's not that tough. Maximum 2 to 2.5 hours video is there. Okay, if you want, you can watch it. Otherwise, after finishing the portion, I can take up the session for that. It's not very tough. It's very simple. Just few basic rules you have to keep in mind. Okay, so when you have 2 carboxylic group present at the same carbon, 1 carbon atom is present between the 2 carboxylic group, and we are heating it, then 1 CO2 molecules eliminates. So consider this, suppose this CO2 comes out from this CO2. This H will come over here onto this carbon atom. So it becomes CH2, and this COOH will be as it is, COOH. Okay. Now when you heat this again, then what happens? Dehydration takes place, right? So RCH double bond CH, COOH is the product here. Clear? Okay, so if this R is phenyl benzaldehyde, if you are taking, then this group is again cinnamic acid we get here. So this is Knovenagal reaction, reaction of aldehyde with active methylene group. So in all these reactions, if you try to compare this, we are having different reagents which creates or which forms a nucleophile, and that nucleophile attacks on the carbonyl carbon. That is what happening in all these reactions. If you see, you just need to know that what name reactions gives you what particular reagent you require, and how do we get the nucleophile into this one. Okay, so basically if you know the reagent, after that's very simple. Like you see, it's 5-pyridine, a base we have, right? And this hydrogen is acidic because 2 electron withdrawing group. So obviously this base will take this hydrogen H plus out, take this H plus and forms the nucleophile. It retracts into this, and then after this is simple. Copied? Okay. Now the next reaction, write down. It is Reformatsky reaction. FORMATSKY, Reformatsky reaction. write down it is the reaction of aldehyde or ketone it is the reaction of aldehyde or ketone with alpha halo ester.
So can you repeat that?
Yes, reaction of aldehyde or ketone with alpha halo ester. With alpha halo ester. Okay. See this. Suppose I am taking benzaldehyde, pH, C double bond OH, plus ester we have, and at alpha position we have halogen present. Suppose we have Br here, alpha halo ester. The reagent we use here is the first reagent we use here, zinc in the first step, and in the second step we use acidic hydrolysis and we are heating it. Okay, this is the reagent we have. So what we get here as A and B, that we'll see. Now zinc is what? Zinc is a metal. And what is the property of metal? Metal gives free electron in the reaction, okay? 2 electron. And we know in presence of free electron, the carbon halogen bond becomes weak. So this alpha halo ester, which is Br CH2 C double bond O OET in presence of free electron. Again, you see we are getting a nucleophile here. From this Br minus goes out and we get CH2 negative charge C double bond O OET plus Br minus. After this, what happens? Could you tell me? After this, what happens?
So it'll attack at the carbonyl.
Yes, you get a nucleophile and this nucleophile attacks onto the carbonyl carbon. So the reaction is, further the reaction is pH C double bond OH plus CH2 C double bond O OET. This attacks onto this, converts into pH CO minus H CH2 C double bond O OET, right? And with H plus H2O, obviously this OET also, this bond also break, we'll get here OH, and here also we get OH, okay? So pH CH, I'll write down in one single step only, OH on the top, CH2 C double bond OOH, and we'll get ETOH out. And then since we are heating it also, dehydration takes place and we get cinnamic acid as the final product.
So A is the structure with the negative on the oxygen. Right?
Sorry, just a second. Yeah, tell me. Yeah.
So A is the structure with the oxygen with the.
Yeah, this one. A is this. A is H plus H2 we are using here, no? So A is this one. This ion. Just a second. Yeah, A is this one. This one. This is A. And this is B. Yeah. Okay, so this is Reformatsky. Zinc with acidic hydrolysis. reaction of aldehyde and ketone. Write down the product in this reaction, and I want you to write down in one single step. Don't try to write down the mechanism. You can
Wait,
take
so
the
1
reference
second.
of this. Achha. You can take the reference of this mechanism, but try to write down in one step. Direct.
Done, sir.
Done? Okay. Write down the product here. Question is, we have double bond O with Br, CH2, C double bond O, OET, and the reagent, what reagent we have here? Zinc in the first step, then H plus H2O, and we are heating it. Write down the product here. Done? Okay. So what happens first of all, it's very simple. The carbon which is attached with halogen will get a negative charge here, carbon ion, and this carbon attacks on this carbon, right? So first of all, we'll write this. We'll have a ring O minus CH2 C double bond O OET. Then with H plus H2O, we'll get here OH. Right, with H plus H2O, we'll get here COOH. COOH. And then when we heat this, this H and this OH goes out, and the product is this. Correct?
So is it possible for the dehydration to happen on the other place also, like inside the ring double bond?
Possible, but that we won't consider because here again the pi bond is in resonance, pi sigma pi. So major is this. We only write this product.
Okay, sir.
Okay. In this reaction, intramolecular also possible. Like you see this one, C double bond O, OET with CH, Br present here on this carbon, then CH2, CH2, C double bond O, H with zinc, H plus H2O, and we are heating it. Tell me the product here. Okay, so what happens in this? The carbon which is attached with the halogen will get the negative charge, right? And this carbon will attack onto this carbon. Okay, aldehyde. So if I number this 1, 2, 3, 4, 5, 6. So we'll get a 6-membered ring in which the first carbon has OH, and this is also attached with the 6th carbon, which has C double bond O, OET attached to it, right? Then when you heat this with H2O, it converts into a double bond here, then C double bond O, OH. Is it? Okay. Next reaction is TiSCHENKO, Tischenko reaction. Tischenko reaction. In this one, we take 2 molecules of aldehyde, RC double bond OH, and it is allowed to react with aluminium ethoxide, OET whole thrice. And it converts into RC double bond O, OCH2R. This is the product we get. So aldehyde, 2 molecules, converts into an ester with aluminium ethoxide. Aluminium ethoxide. Okay, we'll discuss the mechanism in this. Okay, how to do the mechanism. Mechanism is a bit typical into this one, right? So we'll discuss once. Okay, not that important, but we'll have an alternate way to write down the product. Okay, what is that alternate way? We'll see that first. Okay, suppose we have 2 molecules of it, RC double bond OH. Right, so we are taking 2 molecules, RC double bond OH. So what you do, you write down the oxidized product of the one and reduced product of the other one. One oxidation, other one reduction. So acid on oxidation gives what? Sorry, aldehyde on oxidation gives acid. Aldehyde on reduction gives alcohol, right? So OH, CH2, R. Right? OHCH2R. Okay, after this, we are heating this also. When you heat this, then H2O eliminates from this, and these two combines forms RC double bond O, OCH2. This is the product we get. So you always write down the product like this. One oxidation, other one reduction, and then elimination of water molecule by both. Done. Okay. Now you look at the mechanism of this reaction. Are you done? So this is the trick we use, the method to write down the product. The mechanism of this reaction see, aluminium ethoxide in this molecule AlOET thrice, this has one vacant orbital. Aluminium has vacant orbital into this. So this aldehyde RC double bond O in the first step, it donates its lone pair to the vacant orbital of aluminium. Okay, and this converts into RC double bond O Al OET whole thrice, negative, positive, and H. Then oxygen drags the electron pair and we get the carbocation here, AlOET whole thrice. So this is the positive charge we get and negative charge we have here. Okay. Now the another molecule RC double bond O H. This as a nucleophile lone pair on the carbon, on the oxygen, it attacks onto this carbon atom. Okay, and it converts into RCH double bond O positive charge, and this O is attached with this carbon, which has one R group this side, another hydrogen this side, O Al OET whole thrice negative. Okay. Now here what happens, this bond, when you heat this bond breaks, it comes here, forms a pi bond, H minus comes out from this, and this H minus attacks onto this oxygen. Oh, sorry, not oxygen. I did not write one step here. I'll write down here on just a second. This pi bond won't be there because you can consider this comes here and attacks onto this. So we'll have a positive charge here onto this carbon atom. Okay. And this hydrogen, it attacks on the positive charge carbon here. So it converts into RCH2 O C double bond O R and AlOET whole thrice goes out. This is the ester we have. See, mechanism is a bit different like we did in the other reaction. That's why mechanism is not at all important in this reaction. Okay, you just need to know how to write down the product. So one oxidation, one reduction, and then dehydration.
So,
yes.
So, like in the first step, the lone pair is going to vacant orbital. But why will that happen? Isn't oxygen more electronegative than aluminium?
Yes, oxygen is more electronegative, but aluminium has vacant orbital, right? And if you are having this, see, it is a reaction mixture, no?
Yes.
So you are having that reaction condition. Temperature is also there. It is not, that the normal temperature where the oxygen with lone pair is stable. We have a little bit higher temperature. So this electron, it excites into the vacant orbital of aluminium. Aluminium can easily take this electron pair because of vacant orbital. Its octet is also not complete. Only 6 electrons it has. So aluminium tries to gain its octet, and hence it takes the electron pair from oxygen here.
Okay, sir.
Okay, that's how it happens. So aldehyde converts into an ester in this reaction. The name of the reaction is what? Tischenko reaction. Okay. Reaction is, you cannot ignore this. It's important, not very important, but yes, they have asked question on this also. Okay. So you must remember 2 molecules oxidize, reduce product, you write down, eliminate water molecule, you'll get the answer. Right. One more thing you see, RCHO converts into RCH2OCOR. Okay. So based on this, you try to write down the product in this particular reaction. Suppose we have the reaction, we have here 2 molecules of this with AlOET3. Tell me the product. Done. So what we'll do, we'll write down one oxidized product of it. That is C double bond O, OH. Reduced product of this, CH2, OH. And then dehydration. So this will be CH2, C double bond O, OR. Okay. In this intramolecular reaction also possible. Suppose we have this C double bond O, H, and here we have CH2, 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 4 times carbon, C double bond OH with AlOET3. Tell me the product in this one. AlOET whole price.
So could you go to the previous slide just 1 second?
Yes. Okay. Okay, yes. So first of all, we'll write down one side oxidation, C double bond OOH, CH2, 4, and COH, H2. Right? So 4 carbon, 5, total 6 carbon, and 1 oxygen present in the ring, right? When H2O goes out into this intramolecular. So we have a 7-membered ring. And double bond O present here at the adjacent carbon. Clear? Okay.
So can you go to the
Next.
previous slide for 1 second? Yes, sir.
1 second. Okay. Next, write down. Okay. Benzoin condensation reaction. Benzoin condensation reaction. In this reaction, 2 molecules of aldehyde, benzaldehyde here we are taking, is allowed to react with KCN, and the product is PHCHOH, and we have C double bond O PH. Okay, how the reaction proceeds, the mechanism you see, PHC double bond OH, nucleophile is clear, that is CN minus. Okay, this attacks on the carbonyl carbon, pi electron moves up, converts into PH, CH, CN, O minus. Okay, now the next step, this hydrogen H plus, this comes over here, this is proton exchange. So we get PH, COH, CN, and a lone pair negative charge on it. Okay, this is the nucleophile for the another molecule, PHC double bond OH. This attacks onto this carbon and it converts into PHCH O minus CHO minus, okay, COH, PH and CN. Again, we have here proton exchange. H plus comes over here, converts into PH, CHOH, CO minus, PH and CN. Then when this lone pair converts into pi, CN minus comes out as a leaving group. So PH, CH, OH, C double bond O, pH. This is the product of this reaction. So Cn minus KCl here, it is behaving as a catalyst. Not that important. Done. Okay. Now here, one last name reaction in this is, write down Michael addition. Michael addition reaction. This reaction is 1,4 addition in conjugated carbonyl compound. In conjugated carbonyl compound. 1,4 addition. For example, RC double bond O, CH2, CH2, R. This is also the reaction of active methylene group with conjugated carbonyl compound, like in this one you see. C double bond OR. This is conjugated carbonyl compound, right? This R could be, you can take it as hydrogen, or you can take it as OR also. Okay, so this is allowed to react with a base. Again, we have a base, active methylene group gives hydrogen, we get a negative charge carbon here. This carbon attacks on this molecule. But where it will attack? It attacks on this position. This pi electron shift over here and this goes over here, right? So this is first position, this oxygen. This is 1, this is 2, this is 3, this is 4. 1,4 addition we are talking about. Okay. So in this one you see, first of all, with the base, we get a nucleophile, RC double bond O, CH negative, C double bond OR, and this negative charge, this attacks on the fourth carbon, pi shift here, and this pi comes up onto this oxygen, right? So this converts into CH3, CH, O minus and R here, right? So if I write down this side, this would be CH, CH single bond, CH double bond, COH, R, and this carbon has one CH3 this side, and this has two groups, C double bond O, R, C double bond O, R. This with the base which takes this H plus forms BH, suppose. This O minus takes this hydrogen from this. You'll get OH here. Base I'm taking B minus, suppose here. Correct. Now, in this, we'll write down the tautomer of it. This pi shifts over here. H comes onto this carbon atom. So we'll get R, C double bond O, CH, C double bond OR, CH, then CH2, C double bond O, R, and here we have CH3. Okay, this is the product we have. We are just using the base here. Now you see, if this R is OR, then here also we'll get OR and OR. After this base, if you take H plus H2O, then this OR converts into OH here. Suppose after that, if you are heating also here, then this COH, when you heat, CO2 comes out and will end up getting here one acid group, that is COH. Okay, so based on this, we'll see one question. First, we copied on this. You see the addition takes place at fourth carbon. First and fourth carbon takes part in the reaction. Hydrogen first shift onto the fourth carbon and the group attached on the fourth carbon. First oxygen and fourth carbon. Okay. Now, after this, if you have H plus H2O in heat, then what happens? Based on that, we'll see one question. Write down the product in this reaction. We have double bond O, conjugated aldehyde or ketone. So you see it is conjugated. Pi sigma pi conjugation is there. Conjugated aldehyde and ketone with active methylene group. So C double bond O, OET, C double bond O, OET. OET is the ester here, leaving group. So we'll take ET O minus and ET OH is the solvent here. First step. Second step, we are having H plus H2O and we are heating it. Done? Yes, nothing you can do, Richard, because these are name reactions. Okay, so you should even know the reactant and reagent that we are using. So name reaction, you cannot do much. You have to memorize this. First 4 or 5 reaction that we have done is very important. Okay, these are, you can go through once. Okay, not that important. Okay, so here what happens, this negative charge, this will attack on the 4th carbon, correct? 4th carbon is this 1, 2, 3, 4. Excuse me. 1, 2, 3, and 4. So if this attacks here, this pi shift here, this pi shift here. So we get here O minus on the top, double bond, CH2, this CH, C double bond O, OET, C double bond O, OET. And then after this ETOH, the base, this converts into, O minus converts into OH with H plus H2O. With H plus H2O, this converts into OH, OH, right? We'll get this OH, OH, and then again we are heating it. So heating effect, CO2 eliminates from this. So we convert this, this converts into double bond OH, CH2, CH2, COH. Okay, this is the product we get. After this, we can write down the enol form, keto form of it. Double bond O, double bond CH. Oh, just a second. Double bond O, then CH2, CH2, COH. Okay. So this comes over here and this hydrogen gets attached onto this here. This is the product we get. Okay. So this is Michael addition. 1,4 addition, Michael addition it is. So these are the name reactions we have done of this carbonyl compound chapters, that is aldehyde, ketone, and carboxylic acid also. Aldehyde, ketone, many reactions we have done in oxidation reduction chapter. Still there are a few reactions left that we'll continue with, okay, of aldehyde and ketone, and few reactions of acid also, carboxylic acid also we see. Okay, so nucleophilic addition we have done. Okay. So name reaction we are done with. Next start with we'll see some reactions, the nucleophilic addition reactions of aldehyde and ketone. Heading you write down nucleophilic addition. It is not addition elimination. Nucleophilic addition. Addition reaction. Okay. First one, the reaction with NaCN. What is the nucleophile here? What is the nucleophile?
Cn minus.
Cn minus. If Cn minus is the nucleophile, then what is the solvent we should take?
HCl.
HCN.
HCN.
NaCN with plus HCN, the solvent. Reaction we already know the mechanism, you can understand it easily, right? We just go through it. So if this is allowed to react with, if you see this NaCN, NaCN dissociates into Na plus and Cn minus, C triple bond N, one lone pair on nitrogen, lone pair on carbon, negative charge on it. Okay, this is ambidentate ligand. Okay, if you have a little bit of idea of coordination compound, okay, ligands are electron pair donor, right? Ambidentate ligands are what? What are
Give you
ambidentate
one pair.
ligands?
Oh, sorry,
Which
they
has
can
more than
connect
one-
from both sides.
More than one donor side, correct?
Yeah.
Right?
Yes.
So carbon has lone pair, it can donate. Nitrogen has lone pair, this can also donate, right? That's why it is ambidentate ligand. So if carbon donates, then it forms cyanide. If nitrogen donates, then it forms isocyanide. Okay, but usually we know this fact that carbon is less electronegative. So the tendency for carbon to donate electron is more than to that of nitrogen. That's why mainly we get here cyanide as the product. Okay, so now you see if this is allowed to react with RC double bond OR plus reaction of this will write down NaCN with HCN. Could you tell me the product in this reaction? Cn minus attacks onto this carbonyl carbon. It converts into RCO minus R and Cn, which gets protonates from the solvent, converts into RCOH, R and Cn here. Right? So you see the carbon has Cn and OH present onto it. Yes, Varun, correct. This molecule is what? This molecule is cyanohydrin. Biomolecules, we have discussed this. right? Cyanohydrin, CN and OH present on the same carbon. Cyanohydrin, right? Right? One note you write down, isocyanide also forms in this reaction. As a minor product. Okay, isocyanide also forms, but as a minor product into this. So all these are very simple one mechanism we have discussed. Same thing we have here. Now, cyanohydrin, one reaction is very important here. Okay, like you see, if this reaction is allowed to, this molecule is allowed to react with two different compounds. For example, I am adding here NH3. And here I am adding H plus H2, acidic hydrolysis and ammonia. Ammonia, this is lone pair on it. And here we have OH, correct? So what happens with ammonia? Nitrogen-hydrogen bond is polar. In ammonia, what happens? NH bond is polar in nature. Nitrogen is electronegative also. So this H plus, it can donate to this oxygen, which has lone pair present on it. So this H plus protonates this hydroxy group, H2O goes out, and then what happens here, R with carbon here, NH2 get attached on the top, CN and the another alkyl group will be as it is, plus H2O goes out. With ammonia, this reaction takes place. With H plus H2O, this cyanide on acidic hydrolysis, must remember this is important. Cyanide on acidic hydrolysis, it converts into an acid, that is COOH. This COOH, if you, I'll discuss this in the next page, converts into COOH. Okay, this also, if you add H plus H2O, this CN again converts into COOH. So CnH2 RCOOH. So cyanide on acidic hydrolysis converts into acid. Okay, now you see this here. Suppose we have a cyanohydrin, CS3CH, OH, and CN, for example. This on acidic hydrolysis. And then the product that we get, we are heating it in presence of an acid. This with NH3, and the product that we get here, we are doing the acidic hydrolysis of it. Write down the product in these reactions. So it goes under acidic hydrolysis, gives you acid. Sorry, yeah, acidic hydrolysis gives you acid. So this gives you CH3, CHOH as it is, and it is COOH. When you do acidic hydrolysis of this, sorry, when you heat this in presence of an acid, then we get CH2 double bond CHCOOH. Right, it gets protonates, H2O goes out, we'll get a positive charge here. And then from this carbon, alpha carbon, H plus comes out to maintain the concentration of acid. We'll get a double bond here. Okay. Protonates, H2O goes out, positive charge, H plus comes out, we'll get a double bond here between the two carbon atoms.
So, but why does cyanide become into an acid on H plus H2?
Cyanide into acid.
Yes, sir.
I'll discuss. See, suppose you have RCN, correct? RC triple bond N with H plus H2O. So with H plus, what happens? This nitrogen gets protonate. RC double bond NH. Can I write down this directly here, the positive charge? Okay, this pi electron shift here. Then this water behaves as a nucleophile. It attacks onto the carbon. RC double bond NH, OH, and H plus goes out. I'm writing it down directly.
Yes, sir.
Okay, now the same thing again. With H plus, again this nitrogen gets protonate, and we get again RC single bond, NH2 positive charge, 1 OH we already have here. Then H2O again attacks onto the carbon, we'll get RC OH, OH, NH2. Okay, then again nitrogen protonates, forms NH3 plus, NH3 goes out, RCOH, OH, NH3 plus, then NH3 eliminates, will get positive charge on the carbon atom, OH, OH positive charge plus NH3, and then this H plus comes out, leaving this bond pair behind.
So this is for the NH3 part,
Sorry?
right? So this
Sorry?
is for the NH3 part, right? This entire thing.
Come again, Richard. Hello?
So this is Rahul, sir. So like I got
Rahul, tell me,
disconnected
yeah.
in the middle. So this part is for the NH3 reaction.
This part you're talking about?
Yeah.
See, what happens here, actually the same thing is happening step by step. First nitrogen protonates, then attack of water as a nucleophile, you get this. Again nitrogen protonates,
Yes, sir.
attacks of water as a nucleophile, here you'll get this. Again nitrogen protonates, you'll get this. And then from here, this nitrogen has positive charge, it takes this electron pair, goes out as NH3, we get a positive charge here on the carbon atom. And at the same time, carbon has 2 OH group, which is not stable. So easily H plus comes out from this and we get C double bond OH.
Okay, sir.
So in the last step, nitrogen
Thank you,
NH3 eliminates. Just a second. Okay, that's why RCN converts into RCOOH under acidic hydrolysis. Must remember this. Okay. Now here you see this NH3 with this converts into CH3, CH, NH2, CN. Again with this, it converts into COOH here, that you write it down. Okay, you look at this question here. We have cyclohexanone, double bond O, reacts with NaCN, HCN, gives A, H plus H2O, gives B, and next we have 2 molecules of B we are taking. We heat this and we get C. Try this. What happened here? What is it out? Okay. Diester. Yeah, diester will get for C. Yeah, that's correct. In C, you'll get diester. Tell me the product. What is A? A is cyanohydrin. So the carbon which has double bond O converts into OH and CN here. With H plus H2O, CN converts into acid. So on the top we have COOH and OH. What about C? We are taking 2 molecules of it. So you see this. 2 molecules of H2O goes out. OH, COOH. And the another molecule is this. We have COOH and OH. Correct. So H2O comes out and it converts into C double bond O, C double bond O, and this we get here. 6-member single bond. This is okay. Diester we get. Okay. Cyanohydrin on reduction gives amines. Okay, 1 degree amines. One sec. So on reduction cyanohydrins, for example, you see R1 COH, R2 CN. If this is allowed to reduce with LiAlH4, or you take H2PT for reduction reaction, both gives you 1 degree amine as the reduced product. R2 CH2 NH2. Okay. Got it? So this is it for the reaction of NaCN, formation of cyanohydrin, okay, and the product that we get into this, okay. Another reaction is the addition reaction of H2O. This one is important, okay. H2O reaction, it actually does not react with water, LiAlH4, but in case of chloral, the reaction is possible. Okay, why? I'll tell you the exact thing I'll tell you in the next class, the reason behind this. So basically, aldehyde and ketone does not react with water, but if you have chloral is CCl3, C double bond OH. If you have chloral present, then this reacts with water, because the product that you get, it stabilizes through hydrogen bonding, which is this. Okay. So this hydrogen bonding is present. Hence, the reaction of aldehyde with water in presence, in case of chloral is possible. If you take RCHO, then the reaction is not possible. It's very difficult, very slow reaction. What is the reason for this? I'll tell you in the next class. Okay, why I have given you this one? Because this is coming in the test. Okay, one question I told you already. There are, next class we'll finish this. We'll probably finish carboxylic acid also next class. Okay, understood guys?
Yes, sir.
Okay, chalo, take care. Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.